In this module, that is module 3 of chapter 1, we shall learn about the occurrence of Fredholm integral equation. In previous module, we have seen how Volterra integral equation of second kind arises from the solution of initial value problem. Now, we shall see how the boundary value problems give rise to Fredholm integral equation of second kind. Now, we consider the following boundary value problem for an ordinary differential equation of second order, which is given by phi double dash x equal to capital F, which is a function of x and phi x. X lies in the interval 0 to 1. Here double dash means double derivative of phi with respect to x. The boundary conditions are given by phi at x equal to 0 is phi naught and phi at x equal to 1 is phi 1 as given by equation 1.14. Here capital F is an integrable function and phi naught and phi 1 are known constants. Now we will try to get integral equation by solving this boundary value problem. For this, we rewrite the differential equation 1.13 as phi double dash t equal to capital F function of t and phi t, t lies between 0 to 1. We integrate this equation with respect to t from 0 to x to obtain phi dash x equal to capital A plus integral 0 to x capital F t phi t dt. Here A denotes phi dash at x equal to 0. Since in the boundary condition phi dash at x equal to 0 is not given, so it is unknown and consequently A is a constant which is to be determined. Now we integrate again phi dash x to obtain phi x equal to integral from 0 to x integral from 0 to s f t phi t dt ds plus a into x plus phi at x equal to 0. Now, from the boundary condition, we know that phi at x equal to 0 is equal to phi naught. So, we substitute in place of phi at x equal to 0, phi naught. And also, we interchange the order of integration in the double integral in the expression for phi x. This interchange of order of integration is shown in the previous module. Finally, we get phi x equal to integral 0 to x minus t capital F of t phi t dt plus a into x plus phi naught. So, phi x, which was the unknown in the given differential equation, is obtained in equation 1.15. Here we see that the unknown function phi t appears under the sign of integration and also it appears freely. Also in equation 1.15, capital A is unknown. Now if we can know capital A, then phi x can be written in the form 1.15 as an integral equation. Now to obtain A, we use the second boundary condition, that is phi at x equal to 1 is phi 1 as given in equation 1.14. So substituting x equal to 1 in equation 1.15, we obtain A as given in equation 1.16. Now in the equation 1.16, the integral is from 0 to 1. We break this integral into two integrals. First integral will be from 0 to x plus second integral will be from x to 1. And substituting this value of A, we obtain phi x in the form given by minus integral 0 to x t into 1 minus x capital F t phi t dt minus integral x to 1 x into 1 minus t f of t phi t dt plus phi 1 minus phi naught into x plus phi naught. So the integrals 0 to x and x to 1 can be combined to write phi x as phi x equal to minus integral 0 to 1 kxt f of t phi t dt plus phi 1 minus phi naught into x plus phi naught as given by equation 1.17. Here kxt is equal to t into 1 minus x in the integral, first integral, and that is for t less than equal to x, and kxt equal to x into 1 minus t for t greater than equal to x, which is in the second integral. Thus, we see that from equation 1.7, phi x appears freely, also phi appears under the sign of integration, and the range of integration are constants, and there is the term phi 1 minus phi naught x plus phi naught. So equation 1.17 is Fredholm integral equation of second kind, which is non-homogeneous. Thus we see that in general the boundary value problem for ordinary differential equation with boundary conditions can be cast into Fredholm integral equation 1.17 of second kind with its kernel given in the equation 1.18. Now we shall solve some problems concerning ordinary differential equation with boundary conditions and obtain the corresponding Fredholm integral equation of second kind. In problem 1, we consider the differential equation phi double dash x equal to minus lambda phi x with boundary conditions phi at x equal to 0 is phi naught and phi at x equal to 1 is phi 1. Now recall equation 1.13, the general boundary value problem which we have solved. There phi double dash x was equal to capital F of x phi x. Now if we compare 1.19 with 1.13, we observe that capital F of x phi x is equal to minus lambda phi x. Here lambda is a constant. So, following the similar procedure, this boundary value problem 1.19 and 1.20 can be cast into Fredholm integral equation given by equation 1.22. Here, as before, the kernel is equal to t into 1 minus x for t less than equal to x and x into 1 minus t for t greater than equal to x. Now, we observe that in the expression for the kernel kxt, if we interchange x and t, we get the same thing. That means kxt is equal to ktx. So, we can say that kxt is the real symmetric function, and for this reason the integral equation 1.22 is regarded as symmetric integral equation. Next, we go to problem 2. In this problem, the governing differential equation is y double dash x plus lambda yx equal to 0, 0 less than x less than 1, and the boundary condition is given by y at x equal to 0 is 1, but y dash at x equal to 1 minus 2y at x equal to 1 is equal to 2. The governing differential equation is same as 1.19, but here the boundary conditions are more complicated. So, we shall reduce this boundary value problem to Fredholm integral equation of second kind. For this, we rewrite the given differential equation in the form y double dash t plus lambda yt equal to 0. We integrate this equation with respect to t from 0 to x to obtain y dash x plus lambda integral 0 to x yt dt equal to capital A.
Here capital A denotes y dash at x equal to 0, but in the boundary condition y dash at x equal to 0 is not given. So, A is an unknown constant which is to be determined. Now, if we put x equal to 1 in equation 1.24, then we obtain the value of A as y dash 1 plus lambda 0 to 1 yt dt as given in equation 1.25. We again integrate y dash x obtained in the previous equation to get yx plus lambda integral 0 to x ds integral 0 to s yt dt equal to ax plus 1. Here we have used the boundary condition y at x equal to 0 is equal to 1, which is given. Now, we interchange the order of integration in the double integral to obtain yx plus lambda integral 0 to x minus t yt dt equal to ax plus 1 as given in equation 1.26. Here A is still unknown. We have to obtain A. Now, at x equal to 1, equation 1.26 gives y at 1 equal to A plus 1 minus lambda integral 0 to 1 minus t yt dt as given in equation 1.27. Previously, in equation 1.25, we have obtained y dash 1 in terms of A. Now, we use the second boundary condition y dash 1 minus 2y at x equal to 1 equal to 2, and we substitute y dash 1 and y1 obtained previously to get A as minus 4 plus lambda integral 0 to 1 minus twice t yt dt. Now, again in this integral from 0 to 1, we break this into two integrals, that is 0 to 1 will be broken into 0 to x plus x to 1, and we substitute this A in equation 1.26. We make certain simplification to obtain yx equal to 1 minus 4x plus lambda integral 0 to x t into 1 minus twice x yt dt plus lambda integral from x to 1 x into 1 minus twice t yt dt. Now, these two integrals can be combined and we can write yx as 1 minus 4x plus lambda integral 0 to 1 minimum of x and t minus twice xt, this whole thing multiplied by yt dt. Here we see that the kernel of this x integral equation is minimum of xt minus twice xt, and the range of integration is from 0 to 1. So, this is a non-homogeneous Fredholm integral equation of second kind.
With this module, we come to the end of chapter 1. So, let us sum up. In this chapter, we have learned the various forms of integral equation in module 1. In module 2, we have learned how to reduce an initial value problem to Volterra integral equation of second kind, apart from how to get Abel integral equation. Lastly, in module 3, we have learned how to reduce a boundary value problem into Fredholm integral equation of second kind.